Okay, so I wrote this title when I was putting the program together in quite a bit of a hurry, and it sounds like a very grandiose question to be asking, and I don't particularly think that I'm necessarily the best person in the room to answer, but I'm going to have a go because that's in the spirit of the conference. So I am Charlie Kirkwood. Yeah, by background I was an exploration and resource geologist, and then I did work in the mineral exploration industry for a couple of years, and then I worked at the British Geological Survey doing research from there. And then went into data science, realized that a PhD was definitely the way to be going, and I did my PhD here at the University of Exeter in partnership with the Met Office. So I'm maybe also some kind of archaeopteryx, because I've come between geology and meteorology a bit, and with the common theme of data science. And I'm now a research fellow in the Institute for Data Science and AI here. I think we all know this, but why do geological maps matter? Well, geological maps represent our knowledge of the lithosphere, and I think it couldn't be much more important than that. So all of our interactions with the Earth basically depend on this knowledge. So for obtaining materials, harnessing geoenergy, developing our infrastructure, it's all guided by that knowledge. And I think, yeah, in the current state that we're in with the climate in crisis, which we heard from Aline as well, like these are real problems affecting people right now, and I think it's more important than ever that we've got the information we need to be able to make the right decisions, basically. So geological mapping is important. So I think in an ideal world, yeah, maybe we would have a harmonized planetary geological map, which would be able to provide kind of complete and perfect information about the Earth's lithosphere. Like the truth is out there, there is a real state of the geology of the Earth. And we go to all these efforts to try and recover it somehow, to try and represent it in a map. But if we had this kind of perfect map, I guess, which is kind of sci-fi and not likely to actually happen, but then if we could do that, we could query it at any point, and we would just be able to, you know, get answers on what are the geological properties anywhere on Earth and below the surface as well. So then we would, for example, know the exact position and grade of all Earth's resources, and we could optimize how we use them. I mean, that's not the only application, but if we need critical minerals, say, for the green revolution, then it's really going to help if we can be very precise about where they are. But the elephant in the room is that there will always be uncertainty about what's going on in the gaps between our observations. So we make observations at outcrop, or we make observations in drill core, but there's big empty space in between the observations generally, so we have to fill that with an interpretation, and there's a lot of uncertainty associated with that it makes sense to capture as well. So geological mapping, yeah, I'm not going back to Egyptian pharaohs, but William Smith made the kind of recognized first national geological map of any country. I think that's widely recognized, and that was, yeah, the geology of Britain, basically, and this was in 1815. And he did it, or the way that he constructed the map was basically by drawing these lines to delineate different units of rock based on their geological properties. And if we fast forward now to today, then we find that actually the kind of concept for the geological mapping, this hasn't really changed much. It's still about drawing lines to delineate kind of parcels of rock that are sufficiently self-similar that we would classify them as units. So we're just working in terms of lines. But I think the main limitation of this way of working, and we heard it from Christina as well, about the fact that there's classification schemes involved here. So classification of the rocks is based on properties of the rocks, like the age or the lithology, which includes things like the composition and the texture. And these then tend to be continuous variables, actually, but we end up with a discrete representation of the geology because we're constructing a map as a classification. But I think it's basically reality of the situation that no matter how many classes or units we include in the map, we're always going to be losing information, actually, to that discrete representation. So what can these traditional classified maps tell us? Well, if we imagine that we've got a line across the map or across the country, and you can imagine if you had the right tool to measure the property you're interested in, maybe it's the concentration of some critical metal, then there is a true value of that concentration of a critical metal across this transect of the country. So if we knew that true value, we'd be in a great position. We'd know the geology perfectly and everything would be great. But of course we don't know the true value, and all we have are some potentially quite sparse observations. So the challenge is really how do we model those observations and interpolate between them. And if we think about the traditional classified geological maps, then we're basically constructing the map from classes or units that are flat in terms of what they tell us about the geological properties. So as Christina showed us, then you can click on a polygon, say, and you'll get a summary of the age and the lithology and other things as well. But I suppose the spatial variability of what's going on within the polygons is generally not provided, and so then we're dependent on the number of polygons we have to get more fidelity. But as a result, we're losing that information about the spatial variability within the polygons. So another limitation of our traditional maps, and I think probably everyone will agree with this one, is that it's difficult or maybe almost impossible to model and convey the uncertainty involved in making them. Like the decisions that get made and the different judgments by different geologists about classifying one rock type one way or potentially calling it something else, even though it's the same thing. So there is a lot of inherent uncertainty in all of the geological maps that we produce, but in the traditional workflow, it's really difficult to capture that. And there's two types of uncertainty to consider, which would be the map uncertainty or the epistemic uncertainty, due to our lack of knowledge in the system that we're modeling. So you can imagine that we could have drawn the polygons in slightly different positions, basically, and as Christina said, we do end up sometimes with these artificial faults at map sheet boundaries where different geologists have made different decisions about where to draw the boundaries. So there are different possible maps that could be fitted. So there's this uncertainty about where those boundaries should be, which is sort of our epistemic uncertainty in this system. And there's also then the data uncertainty or the aleatoric uncertainty, which is really the variability of observations around the map. So you can imagine there's going to be a distribution of ages, say, distribution of compositions, distribution of textures within each of these polygons, say, and we would want to capture that. And in the traditional workflow, maybe the easiest way to do that would be to dress each polygon with a kind of distribution on top of it to capture that data uncertainty. But we need to essentially capture both of those forms of uncertainty in order to have a good uncertainty quantification. And yeah, to be useful, that uncertainty quantification, it should be calibrated with respect to reality so that, for example, if our mapping system says that there's a 90% chance that a location will have economic grades of a critical metal, we want that to be true in 90% of those cases, and likewise for everything from 0 to 100%, I suppose. So we want to have, yeah, probabilistic calibration with respect to reality, ideally. And it's also useful at the same time to be as specific or sharp as possible, because if we do know very precisely about the geology of one area, then we want to be honest that we have precise knowledge there, but we also want to be honest where we don't have precise knowledge and where there's a lot of uncertainty. And actually, from my PhD, then I've ended up reading about there's quite a lot of literature in weather forecasting about how you can assess the quality of probabilistic forecasts for weather, but I think it's all relevant as well in geology, actually. So I think, and this is just my opinion, and you can disagree if you want, but I think there's two sensible steps for geological mapping in the age of artificial intelligence. So the first is that to satisfy, I think, our increasing need for precision, we should treat geological mapping as a regression problem to predict continuous geological properties as continuous values, and then have the classification be a secondary task on top of that, once we've got these models of the continuous values that the classes are based on. So this illustration here is kind of showing, what that step would look like. We'd move away from the traditional classification into, direct regression of geological properties. And the illustration here is univariate, as in we're imagining on the y-axis that we've got one geological property that we're interested in, which might be shear strength, for example, but it could actually be anything. But also you can picture that the same illustration is kind of relevant if you've got multivariate modeling going on. So we could want to model all of the properties at once, essentially. And you may know this as implicit modeling as opposed to traditional explicit modeling. So in the implicit modeling, then the boundaries between rock types are implied by the modeled geological property values rather than explicitly drawn. And you can picture that if we had a map of the geological properties everywhere in space, then the boundaries that we would like to draw as geologists in the field and so on, we would basically just be putting lines over kind of linear features where the gradient in the properties is really high. But we just got changes from properties that reflect limestone to properties that reflect sandstone, say. And the other thing that I think that we also need to be doing, or that it makes sense to be doing now, and I know that some people have been doing this for actually quite a long time already anyway, is that we should be aiming for uncertainty quantification, and we can do that by treating geological mapping as a Bayesian modeling problem. So we'll model a distribution over maps to represent our knowledge of the geological system. So it could be this or it could be that, and collect new data to refine this knowledge and tighten this distribution to be closer than the truth. And I think in the questions that Christina received, then that was mentioned. The scale of these mapping projects, it's quite difficult, really, I think, to keep them updated as new data comes in. But if we can set up systems to do Bayesian inference, then that can be automated, essentially. And the uncertainty quantification is important because if we just aim to have a single best map, then you don't really know, when you move away from your observations that have been used to construct that map, you don't really know how far away that map is from reality, and that can potentially lead to nasty surprises. But if you're quantifying the uncertainty and entertaining all of the possible interpretations that there could be between your observations, then you're much more resilient to nasty surprises, basically. So here I've put things, I don't know, in a kind of grid to try and picture this. And as well, it would be possible that we just take the classified maps and make those Bayesian already, and then model a distribution of classified maps, essentially. But I don't know if that's actually going to be as useful as heading for direct regression of the properties. Because it seems to me that the direct regression of the properties allows us to get these sharper maps with higher fidelity and higher precision. But maybe this is something that we'll discuss in the conference. And so I did end up putting kind of my thoughts together here, but actually more than my thoughts, because I sort of implemented a system for doing this. And then this I got featured in an article in the Geological Society of London magazine, and it was on the front cover, which was really exciting. And I think, to be honest, this conference might not be happening if that hadn't happened, because maybe a lot of you actually know me from that fact. So in all of what I've said, you could well just be saying, well, isn't this just geostatistics, what you're talking about, and haven't we been doing that for ages anyway? And I think fundamentally the answer is yes, but I think while the progress in the statistical modeling and machine learning and AI side of things has been reasonably steady and incremental, but there have been some breakthroughs as well, like deep learning about 10 years ago. And of course, whilst those methods are developing on the data science side, they're all being supported or even driven by the fact that we've got more and more data available. So I think the amount of data we have today is kind of unimaginably more than we had 10 or 20 years ago. So things that used to be impossible are rapidly becoming possible. So I think, it's an interesting question. Are we now at a point that we can develop statistical modeling, machine learning and AI methods to learn national scale and beyond geological models and maps that are, maybe for the first time, sufficiently geologically plausible to satisfy both statisticians and geologists? And maybe this is just kind of my opinion, but I feel like the two branches have kind of been evolving separately. There's been geological mapping going on for years and years and years, kind of exemplified by William Smith in 1815, but onwards from there, reasonably unchanged for the most part, I think. Meanwhile, there has been geostatistics, which has been evolving as well, but it doesn't seem like they overlap as much as they should, I think. Most countries' geological surveys provide maps that are still like the kind of hand-drawn maps without quantified uncertainty. So somehow, these two fields have been evolving, but they haven't really overlapped. So I think my kind of idea of why it's exciting now in the kind of age of AI is that I feel like those things can be brought together now, and we can have models that will satisfy all of the assumptions that a geologist would want to make. So then eventually geologists won't be able to say, oh, well, they can still say it, they're still fair to say it, but basically we would be able to produce statistically maps that would be completely geologically plausible, as well as sort of potentially really well calibrated and so on. So I think that's why it's really exciting, and that's why this is a really good time to be having this conference, I think. So I wanted to give some really quick examples. I know that we're pretty much up for time, but maybe 5 more minutes and we still get a 20-minute break. So the first one is just a comparison here. This was work I did actually in 2016, but a comparison between ordinary kriging, which is the kind of the fundamental geostatistical interpolation, I guess, versus a random forest on covariates here. So this is for southwest England, actually, which is quite convenient. But unfortunately, Exeter is actually just off the right-hand side of the map, so you can't really see it, but there's the first half of the label. Anyway, so this was modeling soil geochemical data. And yeah, so here's the example with ordinary kriging, but then I was looking at using machine learning and bringing in all the covariate data sets that are available. Can we try and produce a model or an output that is more geologically convincing, as well as hopefully being more accurate? And basically, I found that the answer to that seems to be yes. Like if we bring in the covariate data sets that we've got, and we've increasingly got access to those, then we can learn models, basically, of geological properties that look actually really geologically convincing to a geologist, I think. And well, I say that as someone who did geology to master's level. So in my opinion, this does look geologically convincing. And also, when you do tenfold cross-validation, then the root mean squared error doing this actually was reduced as well. So it seems kind of better in maybe every way, although this doesn't go into the kind of probabilistic calibration and uncertainty quantification. Another interesting thing to compare, though, is then when you bring in the geological map to go next to it, and this is the official geological map of the UK directly from the geology viewer of the British Geological Survey. And even within the country, we still seem to have these issues with map tile boundaries because different geologists have mapped different parts. So someone over here thought that there was a lot of this one that's coloured in green, whereas someone over here didn't think there's much of it, and there's this here and this here and this here. Anyway, so I know from experience at the Geological Survey that this harmonising of maps is extremely important. And maybe the machine learning way forward would help there actually quite a lot. And the other example, which would be really, really quick, is the more recent work that I've done, which was, Bayesian deep learning, published in the paper Bayesian deep learning for spatial interpolation in the presence of auxiliary information. And this is also the kind of workings behind the magazine article. So here, basically, we're doing deep learning, but rather than just learning a single best map, we're learning a distribution over plausible maps. And this is all according to Bayes' rule, and then the formula here shows you how to construct the Bayesian posterior predictive distribution, which is basically this, you can sample different maps from it, so it's like an ensemble over geological maps consisting of P of m given y, which is a posterior distribution over maps, basically, and then each of those has its own likelihood distribution, which gives us the data uncertainty as well, whereas the distribution over maps gives us the epistemic uncertainty. Anyway, this is clearly too quickly to explain it properly, but I've got a poster that I can help to explain later. But this allows us then to learn a posterior distribution over maps from which we can sample plausible maps, and we can do that potentially for multiple properties at once. So for here, it's potassium in red, iron in green, and calcium in blue, and those are in stream sediments collected across the UK, which is one of the most extensive geological properties data sets we have in the UK, basically. So you can go through those and see that we've got basically different maps that you can sample from the posterior. So we're modeling a distribution over maps that reflects our uncertainty. And when you look at how this performs in terms of an assessment on held out data, it turned out to be, well, maybe even surprisingly good. You're welcome to go and test it and try and show that I did something wrong, but I think that I didn't. So one of the interesting things is that the simulated maps actually have spatial autocorrelation properties that are really similar to those of the held-out test observations. So these blue lines here are all different simulated maps, and the variograms, even though there is no kind of length scale parameter in the model because it's a deep neural network, but even so, the simulations seem to have spatial autocorrelation properties that are quite convincing. At the same time, if you take the mean of that predicted distribution over maps, which is what's shown on the right, you get something that looks really detailed and really high fidelity, but also you can check it against held out test data and find that it does actually explain a high proportion of the variance in the data. So the R squared values are, well, sort of up around 0.7-ish, which seems quite good for a natural system that's, I don't know, it's got a lot of variability in it. And also, if you look at the calibration, here's the QQ plot, and it seems to be getting it really well. So it really does seem to be predicting, if it says there's a 90% chance of the concentration of calcium being over some certain threshold, then we really do find that to be the case in 90% of examples. So thanks for listening, and any questions? I did promise a 20-minute break, which means that we'd have to stop right now. I guess you can ask the questions later at my poster if you want. But again, thanks so much for coming to the conference, and I hope you have a great time. And let's just remember, we live on this planet. We need to understand it as best as possible to make the right decisions. So yeah, that's the way to end. Thanks. Time really.
Anyone? Well, a couple of questions.
All right, maybe one quick question if anyone wants one quick question.
Thanks, Charlie. Fantastic.
Thanks.
Do you see, what applications do you see for the uncertainty estimation that you get from these maps that you produce?
Well, I think it can feed into decision making for almost everything, I think. Literally, probably almost anything. I mean, I imagine if we had those maps like that in the kind of probabilistic ensembles for like mechanical properties, then if you're designing a tunnel and you want to know what's the chances of the tunnel collapsing at some point if you don't put in some reinforcement, it's going to give you a probability for that, or you'll be able to derive a probability for that, I think. And likewise, if you could do that globally, say, and you want to look at critical mineral deposits, then if you've got those kind of, probability distributions, then that would allow us to, I guess, go for the ones that are least risky, if that's the right thing to do, which it could well be. Yeah. Thanks.
Thank you.
Okay. Thanks, Emily. Thanks. Should we go to break? But another question. Well, do you want to ask me in the break, or? I don't know. I think everyone deserves a coffee. Sorry, we went 5 minutes too long. So let's leave it at that. Thanks.